the Oregon State Mars Rover team is proud to exhibit our most advanced, capable, and reliable rover to date. We have further developed and refined our systems to tackle this year's URC competition tasks. For the equipment servicing task, our rover will be outfitted with a 6-degree of freedom arm and grasping end effector. Our arm has encoders and strain wave gearboxes at each joint to provide accurate positional feedback and reduce backlash. A camera, distance sensor, laser, and force sensor integrated into the gripper relay situational data back to the base station. The gripper and the arm will be controlled as part of a larger RS-485 communication network, running a custom, reliable signal protocol based on Modbus. We've practiced on equipment servicing mock-ups to ensure our team is competition ready. Our arm can lift and transport heavy objects, as well as manipulate handles and joysticks. Our gripper geometry keeps the fingertips parallel throughout the entire grasping range, allowing it to perform precise actions, such as tightening a screw, flipping switches, and plugging in a USB stick. To further improve the robot's capability in dexterous tasks, we're developing inverse kinematics, allowing the operator to focus on the position of the gripper in 3D space, instead of positioning each joint individually. Our modified rocker bogie geometry maximizes the number of wheels in contact with drive surfaces to ensure the rover can surmount uneven terrain and large obstacles. The low-pressure pneumatic wheels and custom rubber tread increase traction and conform to rough topography. An IMU in the electronics box provides pitch and roll positions to the operators to ensure the rover is operating in a safe orientation. We have 3 cameras with active resolution adjustment based on available bandwidth located on the tower, at the front of the chassis, and underneath the e-box to provide multiple perspectives of the rover's environment. In its full competition configuration, the rover can drive over harsh terrain and operate the arm even in challenging positions. Our Ubiquity Rocket M2 radio has been tested at ranges over 1 kilometer with line of sight and up to 800 meters non-line of sight, allowing us to relay critical systems information remotely to our base station.
Our rover is equipped with a Z stereoscopic camera to sense depth, an IMU for absolute orientation, a GPS for locational accuracy, and encoders for wheel odometry. These devices work cohesively to provide the necessary data for waypoint navigation, obstacle detection, and object avoidance. This sensor data is fed through a dual extended Kalman filter for transforming and fusing odometry sources and RGBD SLAM for autonomous navigation. Waypoints are initially entered from the base station and are then buffered for global path planning. Using the Z camera, our rover can detect and follow AR tags up to 6.6 meters away, as well as generate a point cloud and occupancy grid for obstacles up to 10 meters away.
Our science mechanism performs in situ tests to determine the habitability and presence of life at numerous locations. The sensor array contains a soil health probe, pH probe, microscope, and spectrometer. The sensor array is attached to a linear motion system descending to penetrate the soil during testing. An auger collects soil into the mechanism, where it is then funneled into 8 test tubes for each of the 4 sampling sites. A carousel moves the tubes between soil filling, solution dispensing, and observation stations. Using a theory of environmental degradation, we can determine the existency, extinctancy, or non-presence of life. We will base our judgment on what forms of biomolecules are present or absent, as well as what metabolic byproducts are detected. We will use phthalate solution and iodine to detect carbohydrates, 9-hydrogen to test for amines, fluorescein dye for enzymatic activity, sodom 3 and 4 for lipids, and barium and magnesium chloride to test for sulfates and phosphates respectively. Based on the results of these tests and knowing how long these compounds last in exposed soil, we will be able to draw a conclusion on the status of life in these samples.
These new features will be further tested and improved in the coming months. We look forward to challenging ourselves at URC 2020.